Build this application on top of my fine-tuned singlet model. So let's just try this. For first, we'll try the vision search. Let's say I will pick any of this image. Let's say this one is good sari. And okay, now it must do the vision similarity search. So the sari's result, which is near to this sari, will appear. Let's see the golden sari and the style is copied. So we get the similar sari and mostly the similar fashion as well. Let's try using text only. So suppose I search for green sari. Let's just try using the text only prompt. Suppose I say green sari. So it should bring upon the results which are closer to the image in green sari. And the score you can see here are how much the text embeddings are aligned with the image embeddings. Let's say the score is 0, then the embeddings are perfectly matched. It is kind of opposite here. So these are the results. Suppose I type something wrong. Let's say I type white kurti. Okay. So white kurti. Yes. So white is misspelled and kurti is also misspelled. So this query will first go to query distiller. Query distiller will make the spelling correct and then the embedding search will happen. So the results here are again white kurti. You can see. Okay, now let's just move toward the main reason why I built this kind of application. Suppose this is our sari images and I want some similar sari in purple color, let's say. I will do this. This is alpha. If I make it towards 0, it will be more text focus, and if I will make it towards the 1, it will be more image focus. Now let's just skip to 50 and just try it. So see, the sarees are still purple, and the style is copied, also the golden. So maybe I want it more aligned toward text. Let's say I will do the weightage towards text, and now I'm getting completely purple sarees. Now let's just try to get the semantic meaning of, let's say, some kind of object. If I search for mango, maybe it would become yellow. Yeah, so it is becoming yellow. Let's say I want more flowers on this. So let's try if I can get, yeah, I'm getting the flowers on top. Suppose, let's just see if we could find mains inside. That would be a fun experiment. No, the top results are, maybe I will make it more aligned to a text like this. Oh, yeah, the color is still maintained, but I guess men's sari pictures I don't have. Oh, that's it. That's the search I wanted to implement. Let's try one more. Uh, yeah, let's see. So let's just go to the architecture of the app that I created using fine-tuned LBIT model. So don't judge me by this because it was majorly AI project and the design part I have done it more quickly and not just think a lot about the system. So what the user will do here, he will send a text prompt as well as image prompt, and the image prompt will go to the image encoder, that is vision transformer of ClothClip, and the text will go to the text encoder. For the text encoder, what I found out was like Word and GPT, the clips text encoder do not have semantic understanding, so the prompt has to be clear. So I have added a query distillator which corrects the misspellings and all that things and make the prompt good, so it can easily go to the text encoder of Siglip. Both of these will generate the embeddings based on image and based on text. And as we have done the contrast of pre-training, the image embeddings and text embeddings should be more aligned towards each other. So with that thought, I have decided to take a weighted average of both the embeddings for both vision plus text search that we did when we use image and text both. And alpha, which we were shifting, was this constant, which make it tilted more toward image or more toward text if we do it loose. This one is vision architecture, and anyhow, we will get embeddings at the end of this section, the embeddings. Then so at the end of this, what we are getting are the embeddings. So what I am doing is I'm using that embedding to do the similarity search in the vector space. This is Facebook AI similarity search, and this is vector database. What it does, when I submit it a query which is vector embedding, it will find the closest most similar 5 vector embeddings by their cosine similarity and give out the indexes of that 5 cosine similarity embeddings, and that using that 5 indexes I will search the images in my local database to find that images using the indexes in my local database, and that will return it to the front end. I'm using Python's fast API to handle all these requests within the systems using here, and here I have a logic API which does this fusion of the text embedding. This is called late fusion, and this is how my architecture works. So don't judge me by the architecture. This was a project. Next, I will tell how I managed to train the C-clip model, preserving its catastrophic forgetting and enhancing the result.
Before deep diving into this notebook, I want you to understand why I chose this as a problem statement. So basically, this is the problem with the foundational vision language models like CLIP and CGLIP, that they are heavily trained on Western-centric datasets, and they usually don't have that text-to-image understanding of region-based things, majorly like clothings and food. So to test this, if it is true, I have also run few experiments and found out that these models are really bad to identifying Indian clothings like kurta, sherwani, or lehenga. So my goal is to make this model understand the text to image of Indian clothings, that too with minimal loss in its original knowledge, that is minimal catastrophic forgetting. That's why to make this model understand the Indian clothings, and that too without forgetting its original knowledge, I have decided to perform a clip style contrastive fine tuning on Siglip model. So why I choose Siglip over Clip? I have used Siglip over Clip just for the reason that it uses sigmoid loss rather than a softmax function. What happens with that is it treats every single image text pair as an independent binary classification with dependency on massive batch sizes, and we can achieve state-of-art accuracy on just 32 or 64 batch size. This is why I can train it over GPU, which saves lot of time, and I can use more data to train it. Now let's just deep dive into the notebook. I will first show the configuration that I chose for this model training. I'm using this file, which is the prompts I will generate along the way. I'm using Siglip base with the 16 patch size and 224 input size. The images I chose are from Mesos dataset, which also have this CSV, which contains a lot of information from which I can generate good prompts. Yeah, the image size, this is training batch size. I am using the CUDA device with the Tesla T4 GPU, which has 15.64 GB VRAM. So before training, I have to gather some prompts that likewise I have a lot of images, but I didn't extract the prompt using the labels. So I use the CSV in Measure dataset. Firstly, I filter out the CSV by removing the classes with very less amount of data, or which has null data types, or which images will not open here. I have filtered the data initially, then I do some prompt engineering to build the solid prompts. I use the features that are mentioned in the CSV to create the prompts. I use two methods. One is backup prompt and another is conical evaluation prompts to make the prompt, and another is for the evaluation of the model after training. So after running this, I have got 44,424 prompts with the IDs. This is the final result. This is a step where a lot of ML engineers will not think a lot. This is a train, validation, and test split. To keep it fair, I have done the robust splitting of the class, keeping the percentage of images in each sectors or domains equal. Like I have separated for, let's say for kurtas, I have 80% images for training, 20% for testing, and in secondary split, I split those in 10% validation and 10% test. This will help me to train and get the solid accuracy report. This is a crucial step. Here we can say I am matching the prompts with the image. This block defines the input pipeline for training evaluation. First, I pre-process the prompts using this function and dynamically select the prompt via select text prompt. This acts like a augmentation for text, so that image should not be paired with the same prompt again and again. We have the bag of prompts, so we can use different prompts for same image, so it has the larger context. This fashion dataset function actually loads the image and pair with these prompts while preserving some metadata which we use going forward. A collaborate function, here I batched this image and text using the Cglyphs processor to produce aligned tensor. Finally, when the data loaders are configured, we can start the training. Fine tuning is happening. Using this function, I load the Ceclipse backbone to efficiently move tensors from GPU with non-blocking transfer. I use clip style contrastive loss function where the L2 normalized embeddings are used to compute the cosine similarities, and then apply cross entropy in both image to text and text to image direction to ensure the bidirectional alignment. For evaluation, I use the extract embedding function, which run inference with AMP and outputs normalized embeddings, which are then used in recall K for GPU-based nearest neighbor retrieval. I also include per class K for fine-grained diagnostic and unified run to image evaluation pipeline to ensure consistent reproducible evaluation across checkpoints. So I guess the model is now fine-tuned, and yeah, the training loss is zero point 0.2 and validation loss is 0.4 for second epoch, which is quite good. Let's evaluate the fine-tuned model. Uh, this evaluation is for image to image similarity retrieval, and to our surprise, the improvement is in negative. Like for recall 1, we have minus 0.004, and recall 5 is minus 0.0032. But this one was for the vision search. So let's see in terms of Indian categories, does the vision transformer improved or it's still in loss? So as we can see, the fine-tuned model performs better vision image to image search for some Indian brands while reducing its accuracy for others. We can understand that easily by delta map. We have performed the contrast to parameter efficient fine tuning. So the real test is, can it improve the text to image or text plus image to image retrieval? So I am trying the same evaluation for text to image to do the fair evaluation, and to our surprise, you can see the results. It not only increased, but it increased absurdly for Indian clothing styles. You can see the baseline recall was 0 and it improved till 0.98 for kurta. Similarly for saris, everything. Almost on an average of 57.3%, the retrieval of our fine-tuned model for text to image is perfect. And this experiment is quite successful, and that's why we saw such a good retrieval in our demo app as well. So the text to image retrieval has shown a ridiculous accuracy and recall improvement. But with the vision search, the recall for some Indian brandings were improved, but some it was in negatives. Also, for normal recalls, the accuracy of fine-tuned model is quite below, like it's in negatives. But if you have noticed, it's minus 0.0047 and minus 0.0032 at recall 5. This means at such a less catastrophic forgetting, we have achieved such a huge recall improvement in text to image search. And this is how I conclude this parameter efficient fine tuning, a successful project.